spanning tree. Okay, so a maximum spanning tree is a spanning tree such that the sum of the edge weights is a maximum. So that is just the opposite of minimum spanning tree. Okay, so we can use the Kruskal's algorithm to find a maximum spanning tree. So in the Kruskal's algorithm, if you remember how we built the maximum spanning tree, we sorted the edge weights and we picked the edges of smaller weight and included them in the spanning tree to build the spanning tree, right? So now we do the opposite. Again, we sort the edge weights, but we include the edges of larger weight. So we start with the maximum edge weight and go further down, and that will build as a maximum spanning tree. So that's the only change you have to do to the Kruskal's algorithm. So we can now start with what? Edge weight 15, and that's a maximum. So that will bring together D and E. They are in different components, so now they're the same component. Then you can bring in 11, that's the next largest edge weight. Then you can bring in 9. Again, 9 is between E and G, they are in two different components, so you can bring them together with 9, and then another 9 here, and so on. So just pick the edges now in the decreasing order of edge weights, and what you end up with is a maximum spanning tree. Now in this case, the maximum spanning tree weight is 59. So that means for this given graph, that's the maximum possible weight of a spanning tree that you can come up with for this graph. Okay, so what you should know now is for a given graph with edge weights, you can find both a minimum spanning tree as well as a maximum spanning tree using the same algorithm, Kruskal's algorithm. Okay. Now all the properties that we just went through are also applicable for a maximum spanning tree. So in the lecture we saw how to prove a property for a minimum spanning tree, right? Like this property that we just went through. So you should be able to rewrite things for a maximum spanning tree also. Okay, so if you want to practice that, you can try that. Okay. Now I have given here an alternate approach. Let me just quickly explain what I mean by that. So one approach which I just explained is just sort the edge weights and pick the edges in the decreasing order of edge weights. So in this case you start with 15 and then 11 and then 9 and so on. Now another approach is you could make all edge weights negative, okay, and of course again sort them. Now if you make all the edge weights negative, then you know for negative numbers what's the other way. So in this case, if you make all the edge weights negative, the smallest edge weight is going to be what? Negative 15, right? Because negative 15 is smaller than negative 5. Okay, if they are positive, 5 is less than 15, but if they are negative, negative 15 is smaller than negative 5. So that means if you make all the edge weights negative, or even if there could be negative edge weights to begin with, some edges could have negative weights too. So basically change the sign of all the edge weights, okay, and then run the original Kruskal's algorithm. The original Kruskal's algorithm is to pick what? Edge weights in the increasing order. Start the smallest edge weight and next smallest edge weight and so on. So in that case it will pick negative 15, that will still bring together D and E, then negative 11, that will bring together F and G. So that means if you go through that process of using the original Kruskal's algorithm and picking the edge weights of smaller weights, but everything will be negative, right? So at the end, after you have got a spanning tree of all the vertices, change all the edge sign of all the edge weights. So change all the negative to positive, and if there are some negative positive edge weights, turn them to negative. Okay, so that way you still end up with a maximum spanning tree. So there could be two approaches. Okay, so you could use a very straightforward approach of just picking the maximum edge weights like I just showed here. The other approach is to change the sign of all the edge weights in the given graph, and then run the original Kruskal's algorithm of picking the smallest edge weights. And then once you get to the final spanning tree, just change the sign of all the edge weights in that spanning tree, and that way you can get now a maximum spanning tree. Okay, so both ways you get a maximum spanning tree of weight 59 for this given graph. Right? Any question? You can type it and let me convert this to a small video.